students, I'm back with your next class. In today's class, we are going to discuss population growth. Okay, so see here, the size of the population is never constant, isn't it? And why is it not constant? That's because it keeps on changing depending upon the factors like food availability, predation pressure, and adverse weather. Okay, now this fluctuation in the population size is brought about or controlled by four basic processes. So because the population size is never constant, in certain or the other way it keeps on getting affected. Sometimes due to those reasons the population size may increase or expand, or it might decline as well. This expansion or decline in the population size is under the control of four basic processes. Okay, so what are they? Is natality. Natality means it's the number of births during a given period that are added to the population. Alright, that means the number of birth that's taking place, in short, would be referred as natality. Alright, next is motility. Motility is of course the opposite, that means the death rate. Okay, so it's the number of deaths in the population during a given period of time. Alright, next, immigration. All of you know the meaning of this. So it's the number of individuals of the same species that have come into the habitat from elsewhere. Alright, so if suppose a few members of the same species moves into a habitat, they would be referred as immigrants. They would add up to the population density. Okay, next, emigration. That's the opposite again. It's the number of individuals of the population who left the habitat and had gone elsewhere. Okay, so that means what? From the population, a few members might further go elsewhere as well. Okay, that would again decline or reduce the population density. Alright, so these are the four important factors that would affect the population growth at any given time. Okay, so if we consider that, see here, by these population characters, the density of the population, which is referred as capital N, at the time t can be expressed after a period of time, that is t plus 1, as nt plus 1 is equal to nt plus b plus I minus d plus e. This is the equation by which you can easily estimate the population growth, okay, at any given time. Okay, so nt plus 1 is the population density at a particular given period of time, and nt is the initial density, which is again being determined by these four factors, where b is the number of births, I is the number of immigrants which are being finally added to the population, isn't it? On the other hand, minus d, that is number of deaths, and e, that is emigrants. Okay, number of emigrants. These two are finally getting reduced from the population. Okay, so by this equation, finally you can get an idea regarding the population growth. Okay, now let us discuss the growth models. So first of all, the growth pattern that goes on in a population can be of two types, and they can be represented by two types of growth models. So let us start with the first one. So see here, the growth models represent specific patterns of population growth, and they are of two patterns of growth which can be explained depending on the impact of the environmental factors. Of course, population growth to a great extent would be determined by the environmental factors. So the first growth model that we are going to discuss is the exponential growth. Okay, now first, see, exponential growth, it occurs when the resources are unlimited. Now, in any given habitat, the space and food, when it is unlimited, okay, then we will call it the resources being unlimited. Okay, so exponential growth is also known as geometric growth. Fine. See here, according to Darwin, when the resources are unlimited for a species, the species now can realize fully its innate potential to grow in number. So in a given habitat, in case the food and space or the resources are unlimited, in that case, the organism or any species living there can be reaching out to its maximum growth. Okay, it can reproduce to its maximum extent, hence the population growth would be growing or expanding very rapidly. Okay, see here, this intrinsic rate of natural increase is called biotic potential, which is referred with a small r. Fine. Now, the value of R helps to assess the impact of environmental factors on the population growth. Fine. And following are the important aspects of exponential growth. First, so these aspects or these points that I have written, they all would signify exponential growth and are of huge importance. See the first one. Any increase or decrease in the population, that is n0, during the time t will be denoted by the equation dn by dt, that is change in the population density, okay, or the population size, will be equal to b minus d, where b is the per capita birth rate and d is the per capita death rate. Okay, so dn by dt is equal to b minus d into n. Also, if b minus d is equal to r, in that case the equation becomes dn by dt equal to Rn. Of course, you should remember small r here means biotic potential. Okay, fine. Next aspect, the integral form of the exponential growth equation would be, if the exponential growth equation is this dn by dt equal to Rn. So if you write it in the integral form, it becomes nt is equal to n0 e to the power rt. Okay. Now, any species growing exponentially can reach huge population density in a short time. So, of course, if the habitat is providing unlimited resources, so in that case, of course, the organisms can reach a huge population density in a very short period of time, right? So, the equation dn dt equal to Rn results into a J-shaped growth curve. So, growth curve for exponential growth model would be J-shaped. That means it would begin, suppose it is like this, it is the graph, here the growth would start somewhere from here and it will keep on going straight like this. It would never come to a halt. So if it keeps on moving upward because the resources are unlimited, of course the growth curve becomes J-shaped, isn't it? So for exponential growth model, the growth curve is going to be J-shaped. Alright. Such population stops abruptly due to some environmental resistance when a resource may get depleted. Now when this growth curve will keep on going upward, isn't it? It is never going to stop. Is it like that? No. Everything that increases or it expands has to come to a halt at last, isn't it? So all of a sudden, due to some kind of environmental resistance, this J-shaped growth curve would abruptly come to a stop. Okay, when the resources may start getting depleted due to some environmental factors, the resources which were unlimited in the environment or in the habitat, they suddenly might start to get depleted. It is then that the J-shaped growth curve would abruptly come to a halt. Alright. For example, algal bloom or insect population, which otherwise would show rapid growth, but abruptly their growth would come to a halt. Okay. Last aspect is the magnitude of R. Magnitude of R was 0.0205 in 1981 for human population in India, while in 2001 it reached 0.0176. Alright. Whereas for Norway rat it is 0.015 and for floor beetle it is 0.12. So every species according to their biotic potential or according to how much they can increase over time given the particular resource, or that is food or space provided by the environment, they have a fixed value or magnitude of R, biotic potential. Okay, that means it is the value which signifies the rate of population growth for that particular species in a given habitat. Alright, so this is all about the exponential growth. Next we'll discuss logistic growth model. Now the next growth model we are going to discuss is logistic growth. Okay, so see, in the logistic growth, the biggest difference you will find from exponential growth is that in logistic growth, we will take into account that the habitat do not possess unlimited resource. for every species that it contains, it would be only providing limited resources. That means limited food and space. Okay, and under that limited resources, the species will have to grow. So accordingly, they will compete among each other for the same resource, and while they do so, only the fittest, okay, only the fittest and the strongest will be able to reproduce or survive. Okay? That's the biggest difference on the basis of which exponential and logistic growth curves have been separated. Okay, so see here, the resources present in the habitat are limited. Okay, every habitat has enough resources to support a maximum possible number beyond which no further growth is possible. Okay, so only up till a limit every population would be allowed to grow, but beyond that no population would be able to grow further. Okay, there is a limit. There is a limit that would be provided to every growing species. Okay. Now, this natural limit for that species is going to be known as carrying capacity, which we will be denoting with capital K. Okay, now this leads to the competition for limited resources, and hence only the fittest organisms will be able to survive or reproduce in that habitat. Alright. The sum of environmental factors that limits the population size is called environmental resistance. Okay, so as the population size will keep on increasing, the environmental resistance will also keep increasing. Fine. So it rises with the rise in population size. Now, the influence of environmental resistance for biotic potential is denoted by, so there is a very strict relationship that would be maintained between the carrying capacity and the environmental resistance. Okay, and that's how we'll be denoting it, K minus N divided by K. Alright. Now, the following are the aspects of logistic growth, or these are those points which are very important for your exam. The first one is the population growing under limited resources, that means logistic growth. Initially it will show lag phase, when you very well know, you have learned about it in the planned growth and development chapter, isn't it? That there can be a growth curve which is S-shaped or sigmoid growth curve, isn't it? There we have three phases of growth: the lag phase, the log phase and the stationary phase, right? So the logistic growth curve will also show that same pattern of growth. So here it would possess a lag phase initially when the growth is very, very slow, followed by a phase of acceleration of growth. That's called the log phase or exponential phase also, isn't it? And finally, it would reach a asymptote. That means it will become stationary, and we call it the stationary phase when K is reached. So when the K, carrying capacity for that species, would reach in the habitat, automatically the growth curve would become stationary. No further increase beyond the carrying capacity would be allowed. Understood? Next. Such growth is represented by sigmoid growth curve, which is very obvious by now. And then this type of growth is also called Verhulst-per logistic growth. Very, very important. It's also called Verhulst-per logistic growth. And it is described by the equation dn by dt equal to Rn K minus N divided by K. Okay, so the growth equation for exponential growth was only this much, dn by dt equal to Rn, isn't it? But in logistic growth, additionally K minus N divided by K would be added to the equation. Okay, now the logistic growth model is considered more realistic one. This is very, very important, and I think all of you might have already understood why logistic growth would be more realistic one. That's because no habitat would ever be able to provide unlimited resource to a species, isn't it? Everywhere in nature, the competition among the species would persist, and that's only because they all go after the same resource, and the resources are not going to be unlimited, isn't it? Every environment would provide limited resource, right? And that's why logistic growth is much more realistic in its approach. Fine. So last, we are going to compare the growth curve for both exponential and logistic growth that we have learned so far. And here you can see that this being the population density, and here we plot the time. Accordingly, for exponential growth, the curve has been plotted, or the curve has been denoted with blue. Whereas for logistic growth, it has been denoted by red. So for exponential growth, as the resources are unlimited, that's why the growth curve would keep on increasing, and it will keep on expanding, and hence it would form a J-shaped growth curve. Okay, where A is the growth curve and it is denoted by the equation dN by dt is equal to Rn. Alright, whereas in logistic growth, because we take into consideration that the resources now are limited, so in that case we have three distinct phases in the growth curve, giving it a S shape or sigmoid growth curve. Okay, we have initially a very slow rate of growth called the lag phase, then suddenly it has grown. Okay, then suddenly it has rised up and we call it the log phase, and finally as the carrying capacity. See, this one is the carrying capacity, and you know very well that in logistic growth no species can grow beyond carrying capacity. So as the carrying capacity is being reached, environmental resistance will keep increasing, due to which the population will reach a stationary phase. Understood this? So here the growth equation becomes dN by dt equal to Rn k minus n divided by k. Alright, so this is all about the growth models. Next we'll discuss life history variations. Now let us discuss life history variation. Okay, see, populations evolve to maximize their reproductive fitness in their habitat, isn't it? Every species would want to increase in their number as they survive in their habitat, right? Now, this fitness towards maximizing reproduction is called Darwinian fitness, that is high R value. Okay. Now, according to this, under a particular set of selection pressures, organisms would of course evolve towards the most efficient reproductive strategy. So to maximize their reproduction or to increase in number, they would take up different strategies according to their environment, according to their biotic and abiotic components that they have to interact all the time with. Okay. Now, some of these strategies are as follows. So all these strategies are finally taken up by an organism according to its habitat or according to its environment. Why? To maximize their reproduction. Okay. Now, first strategy is breeding habit. Okay. Some organisms breed only once in their lifetime, like Pacific salmon fish, while the others breed many a times, like most birds and mammals. Likewise, number and size of the offspring. Some produce a large number of small-sized offsprings like oysters or pelagic fish, while the others would produce a small number of large-sized offsprings like the birds and mammals. Fine. Now, these life history traits mainly evolves with respect to the constraints imposed by the abiotic and biotic components of the habitat in which the organism lives. Now, I have already told you these strategies would be taken up by different organisms according to the abiotic and biotic components which it has to interact with continuously while it is present in the habitat. Now, these strategies will finally allow an organism to achieve the Darwinian fitness. So, these strategies will help it to reach the Darwinian fitness or to increase in its number maximum while it survives. Okay, so that is all regarding today's class. In the next class, we'll start with a very, very important part of the chapter from where maximum questions are asked in NEET, and that is population interactions.